Welcome to Sleepy Stories. In this episode, we will take a clear and steady look at space without borders, the vast continuity that surrounds every world and stretches farther than any horizon we can imagine. This story is meant to help you learn while you rest. If sleep doesn't arrive immediately, that is completely fine. You can still enjoy absorbing quiet facts about the universe as your breathing slows and your thoughts begin to settle. Simply listen, let the rhythm of words move at its own pace, and allow the information to drift lightly through your mind. The purpose is calm awareness, not memorization. When rest comes, the science will remain, woven gently into memory. Space appears empty, yet it is not a container with edges. It has no wall to touch, no surface to end upon. Astronomers describe it as a fabric, a continuum that curves and stretches, shaped by gravity and time. Every planet, star, and galaxy is a small concentration within this continuum, floating on a sea that never stops expanding. There is no privileged center, no outside waiting beyond. Space grows everywhere at once, carrying its contents like leaves upon an invisible tide. Long ago, people imagined the universe differently. Before telescopes and equations, the sky was thought to be a roof, a solid dome studded with light. The line where Earth met heaven looked definite, reassuring in its boundary. But each century pulled that dome higher, then dissolved it entirely. Through glass lenses and careful mathematics, the illusion of enclosure faded. The heavens were revealed as depth rather than surface, distance rather than ceiling. The night sky became a window instead of a lid. Today, when we speak of the universe, we mean all space and time together, a single continuum that includes galaxies, radiation, particles, and the forces binding them. The known portion, what we can observe, extends roughly 46 billion light-years in every direction. Beyond that limit, light has not yet had enough time to reach us. But absence of sight is not proof of absence itself. The cosmos does not end where observation stops. It merely recedes beyond our current reach. Physicists use geometry to describe how this boundless space behaves. The equations of relativity show that mass curves space-time, giving rise to gravity. That curvature replaces the notion of invisible tethers pulling on objects. Planets orbit the Sun because the Sun bends the surrounding fabric, and their paths are simply the straightest possible routes within that curvature. Even light follows these curves, its beams bending slightly as they pass near massive bodies. In this way, gravity is not a distant force, but the shape of existence itself. When we say space without borders, we acknowledge this structure, yet also its continuity. There may be regions unreachable, but there is no cosmic wall. You can travel endlessly in any direction and never encounter a final edge. Some models even suggest that if you went far enough, you might return to your starting point, just as a traveler on Earth can circle the globe without finding an end. Boundless does not always mean infinite. Sometimes it means connected without perimeter, finite yet unconfined. As you imagine this expanse, think of stillness rather than motion. Galaxies drift apart, but the change is slow on human scales, so gradual that it resembles quiet breathing. Light crosses the void at constant speed, carrying the history of stars across ages, while the underlying fabric keeps unfolding. The scene is dynamic yet tranquil, immense yet orderly. The same physical laws that govern a falling apple hold steady across a billion light-years. The familiar and the infinite are built from the same code. While you rest, allow these facts to take gentle shape. Picture yourself beneath the true sky, one that no longer ends in a dome but continues endlessly above and below. The darkness is not absence, it is structure too wide for eyes to finish seeing. Every star, every dust cloud, every particle floats within the same unbroken continuum. There is no outside to step beyond, only deeper layers of connection. You do not need to hold the details tightly. Knowledge, like space, expands best when given room. Let the thought of borderless space ease the edges of your own awareness. If drowsiness begins to rise, let it come. If wakefulness lingers, that is equally welcome. In both states, you remain within the same quiet cosmos, sharing its patience and its lawfulness. Space without borders is not a distant idea, it is the condition of everything that exists, including the calm you feel now. For most of human history, the sky felt close and contained. People stood on plains or mountain ridges and saw a perfect curve above them, a hemisphere painted with stars. To their eyes, the heavens looked solid, a crystal vault or a great bowl turned upside down over the earth. This idea appeared in myths from every culture. The Egyptian goddess Nut arched her star-covered body across the world. The Babylonians imagined a firmament of shining metal, separating the waters above from the waters below. Greek philosophers spoke of nested spheres, each carrying a planet or the sun. The sky seemed protective, a ceiling to keep chaos at bay. This early vision was natural. With no instruments to measure distance, people relied on what sight suggested. The stars looked small and equally distant, like beads on the inner surface of a vast shell. The sun moved across that shell by day, and the constellations wheeled predictably by night. The rhythm of those motions brought order to human life. Seasons, calendars, and navigation all depended on the apparent geometry of the dome. The universe, to the ancient mind, was a closed, harmonious system, secure, limited, and comprehensible. Gradually, observation began to fracture that illusion. As scholars recorded planetary positions over centuries, they noticed irregularities that a rigid sphere could not explain. The wandering of Mars, the looping paths of Venus, and the sudden appearance of comets hinted at depth and complexity. Philosophers like Aristarchus suggested that Earth might not be the center at all. Centuries later, Copernicus, Galileo, and Kepler replaced the old crystalline shells with mathematical orbits, revealing a sky in motion, governed by laws rather than myth. When Galileo turned his telescope toward the moon, the transformation became undeniable. Its surface was not smooth or divine, but marked with mountains and craters. The Milky Way, once thought to be a cloudy ribbon, resolved into countless stars, stretching far beyond any crystal sphere. Each new lens showed not a surface but a depth, an unending layering of light. The firmament dissolved into perspective. Still, the habit of boundaries persisted. Even as telescopes improved, many imagined that the stars filled a finite sphere surrounding the solar system. It was only in the early 20th century, when Edwin Hubble measured the distances of faint nebulae, that the truth became clear. Those hazy smudges were entire galaxies, each containing billions of suns, scattered through an expanding universe. The dome of stars was not the edge of anything. It was only the nearest part of a structure without measure. Modern astronomy continues to peel away illusions of containment. The atmosphere once thought to separate heaven and earth is now understood as a thin film around a single planet. Beyond it lies interplanetary space, then interstellar, then intergalactic, layers of emptiness more vast than the distances between ancient cities or continents. The old dome has been replaced by depth upon depth, each scale dwarfing the last. This change in perspective did more than enlarge maps. It changed our sense of belonging. The sky no longer protects by enclosing. It connects by extending. The same stars that guided travelers millennia ago still shine, but we now see them as part of a greater continuum, bound together by gravity and the shared physics of matter and light. Our ancestors looked up and saw boundaries. We look up and see relationships. There is comfort in this evolution. A dome is finite. It ends where it meets the horizon. A universe without borders has no such limit. yet it is not chaotic. Its order comes from simplicity, laws that apply everywhere, from falling apples to orbiting moons, from the pull of tides to the drift of galaxies. The shape of the cosmos is not a wall but a pattern, repeating through scale and time. As you picture this transformation, imagine the dome gently fading into transparency, the stars no longer fixed upon it but suspended in open depth. What once felt like ceiling becomes pathway. What once seemed confining becomes immeasurable. The sky remains the same, yet perception has changed. There is no top, no outer shell, only space continuing without edge. And within that vastness, the human gaze is free to wander, reaching farther with every generation, dissolving one boundary after another in the quiet search for understanding. Every point of light you see in the night sky is a message that has traveled through time. Light moves incredibly fast, about 300,000 kilometers each second, but even at that speed, cosmic distances turn travel into history. The rays reaching your eyes tonight began their journey long before this moment, crossing vast reaches of darkness to bring you a glimpse of what once was. The moon, our nearest companion, offers the gentlest example. Its pale glow is sunlight reflected from a surface just over 1 second away in light travel time. When you look at it, you see the moon not as it is now, but as it was a heartbeat ago. The sun, although seemingly close, is 8 minutes away by light. Each sunrise is already past by the time it arrives. That short delay is insignificant to daily life, but it hints at a deeper truth. Space and time are inseparable, and every distance is also an interval in the past. Extend that idea outward. The light of the nearest stars took years to reach us, the glow of distant galaxies, millions or billions. When astronomers aim telescopes at those faint smudges, they are not photographing the present, they are witnessing the universe at earlier stages of its story. A galaxy 10 billion light-years away shows how it looked when the cosmos was young, its stars just forming, its structures still unsettled. Observing deeper means observing older. Telescopes become time machines, their mirrors collecting not the light of now, but the memories of what has been. Each photon is a courier of information. It carries the imprint of the conditions where it began, the temperature of a star's surface, the composition of its gases, the motion of its host galaxy. When it finally meets a detector or an eye, that information becomes knowledge, a reconstruction of an event that may no longer exist. In this way, astronomy is less about seeing space than about reading light. Every spectrum, every faint color shift, is a sentence written across time. Because light moves at a fixed speed, no faster signal can outrun it. That limitation, once frustrating, defines how we perceive reality. We never see the present in its entirety. We see overlapping layers of the past, converging from different distances. The universe is a grand archive, its shelves arranged by light years. The farther we look, the older the record we read. Even within our own galaxy, this layering is immense. The light from the bright star Deneb, part of the Summer Triangle, left more than 2,000 years ago, around the time ancient philosophers were debating the structure of the cosmos. The Andromeda Galaxy's glow began its journey more than 2 million years ago, when early humans were shaping the first tools. On a clear night, you see that light now, but it began long before humanity existed. You are watching an ancient moment still unfolding, its message finally arriving across the gulf. This awareness reshapes how we think about the sky. It is not a collection of simultaneous events, but a tapestry woven from countless pasts. Some stars we admire tonight may have already exhausted their fuel and faded away, their last light still on the road. Others will shine for ages, their beams continuing long after our age has passed. The night sky, then, is not fixed. It is a living record, a visual history constantly arriving. There is quiet comfort in this realization. To see the universe is to engage in an act of remembrance, to meet the past at the speed of light. It means that every glance upward connects you to billions of years of unfolding creation. The glow that reaches you has crossed unthinkable distances, survived collisions with dust, and slipped through the gravitational pull of galaxies simply to arrive. As you let that thought settle, imagine the darkness around you not as empty, but full of travelers, photons still on their way, carrying the stories of stars yet unseen. Some began their journey before Earth formed, some will continue long after. Every gleam you perceive is a bridge across time, linking this quiet moment to the beginnings of everything. The universe does not rush. It delivers its messages patiently, one beam at a time. And in receiving them, you become part of its continuity, the observer through whom ancient light finally finds a place to rest. Human imagination is naturally drawn to what can be measured. We know the span of an arm, the height of a building, the length of a walk across town. Yet the universe refuses to fit within those simple scales. To move from what is familiar to what is cosmic, we need a new kind of measuring stick, one that grows by powers instead of steps. Scientists call this the logarithmic scale, a way to hold the immense within thought by counting not 1 by 1, but 10 by 10, each level expanding by an order of magnitude. Start with something small, a single grain of sand, perhaps 1 millimeter wide. Line up 10 of them, and you have a centimeter. Multiply again by 100, and you have a meter, the length of a stride. 10 strides make 10 meters. A small room, 100 times more gives a kilometer, about the distance of a short walk. So far, everything feels manageable. But continue multiplying, and familiarity vanishes. 10,000 kilometers spans the Earth's diameter. Multiply again, and you reach the distance to the moon, nearly 400,000 kilometers, more than any traveler has walked or flown since the Apollo missions. Beyond the moon lies a gulf that dwarfs every human journey. The sun sits 150 million kilometers away, and light itself, swift beyond comprehension, needs 8 minutes to cross that span. Multiply again, and you begin to measure the orbits of planets. Mars, Jupiter, Neptune, each an order of magnitude farther. The numbers expand so quickly that words begin to fail. Astronomers switch units, measuring in astronomical units or light years, where distance becomes time and motion becomes history. The nearest star beyond the sun is more than 4 light years away. That means light travels for 4 years, 35 trillion kilometers, before reaching Earth. The galaxy we inhabit, the Milky Way, stretches 100,000 light years across. Within it, hundreds of billions of stars trace orbits around a common center, like dust caught in a glowing spiral. Even this grand structure is only one among billions more, each galaxy scattered through space like floating islands in a cosmic sea. At this point, scale turns into something else, a meditation rather than a number. The logarithmic ladder continues upward, from galaxies to clusters, from clusters to superclusters, until structures span hundreds of millions of light years. What began as the size of a grain of sand has become a framework so vast that it defies intuitive sense. And yet, the same physical laws apply at every level: gravity binding, light traveling, time unfolding. The cosmos is immense, but it is also consistent. Patterns repeat as though the universe enjoys echoing its own design. At microscopic scales, atoms orbit nuclei, much like planets orbit stars. In galaxies, spirals of gas and dust mirror the walls of hurricanes or the shells of sea snails. This repetition across magnitudes suggests that nature works through rhythm and proportion, weaving harmony into the fabric of all things. The infinite does not mean disorder, it means structure so large that comprehension must move gradually, rung by rung. The mind may tire when confronting such distances, but there is calm in acknowledging them. To think of scale is to accept perspective, to recognize both smallness and belonging. You are made of the same matter that forms the largest galaxies, governed by the same principles. In the vast hierarchy of size, no level is less real or less important than another. As you rest with this idea, imagine yourself standing on that ladder of magnitudes, somewhere between the atom and the galaxy, perfectly positioned to perceive both. The immense does not exclude the minute. Each defines the other. From a grain of sand to a supercluster of galaxies, every rung on the scale is a single note in the same grand composition, one that plays not in time, but in space, rising endlessly without ever needing to end. Long before there were stars, before galaxies had formed or planets had coalesced, the universe was filled with light, but not the kind that can be seen through any telescope today. This was the first light, a pale afterglow born from the universe itself. To understand it is to travel back almost 14 billion years, to a time when everything that now exists was compressed into a hot, dense sea of energy and particles. In that early state, light could not travel freely. The universe was opaque, a glowing fog where photons, the particles of light, were trapped, bouncing endlessly from one charged particle to another. Matter and radiation were woven together so tightly that space shimmered with heat. As the universe expanded, it cooled. Roughly 380,000 years after its beginning, temperatures dropped enough for electrons to combine with nuclei, forming neutral atoms. With that single transformation, the fog lifted. Light was released and allowed to move unimpeded for the first time. Those newly freed photons began a journey that has never stopped. Over the billions of years that followed, the expansion of space stretched that ancient radiation into longer wavelengths, transforming it from blinding brilliance into a faint microwave glow. This is what astronomers call the cosmic microwave background, or CMB, the oldest observable light in existence. It fills the universe evenly, arriving from every direction like a whisper that never fades. Though invisible to human eyes, it can be detected by radio telescopes as a gentle hum, a remnant from when the cosmos was only a fraction of its current size. The discovery of this background light in the 1960 seconds was an accident. Two engineers, Arno Penzias and Robert Wilson, were testing a sensitive antenna for satellite communication when they encountered a persistent noise that would not disappear, no matter how they adjusted their equipment. They cleaned the receiver, chased away pigeons nesting inside, and recalibrated every component, yet the signal remained steady, uniform, and coming from every direction. They had stumbled upon the universe's own echo, the afterglow of its birth. When scientists mapped this radiation in detail, they found it astonishingly uniform, yet not perfectly so. Minute variations in temperature, differences of just 1 part in 100,000, were scattered across the sky. Those tiny irregularities became the seeds of structure. Regions slightly denser than average grew under gravity into galaxies, clusters, and eventually the vast cosmic web. The delicate speckles in the CMB are, quite literally, the blueprints of everything that would follow. To look at the cosmic microwave background today is to gaze into the universe's childhood photograph. It shows a time before stars, before chemistry, before even darkness had meaning. Every photon from that era has been traveling ever since, stretched by expansion but never lost. It is remarkable to think that when you tune a television to an empty channel, a small fraction of the static that flickers across the screen comes from this ancient light, an artifact of the moment when the universe first became transparent. This background glow teaches us that the cosmos has a memory. Nothing that once existed is completely gone. It lingers in traces, in radiation, in the quiet energy between galaxies. The CMB is not only scientific evidence, it is continuity made visible. It links every atom, every world, every era, back to that initial moment of clarity when light and matter went their separate ways. As you reflect on this, picture the universe not as darkness punctured by light, but as light gradually revealing darkness. What we call night is simply a place where the first light has traveled too far to be seen by the eye. Yet it remains, flowing through space, touching everything. The glow that began when time itself was young still surrounds you now, softened by age but never extinguished, proof that even beginnings can last forever. Every form of vision has a boundary. Eyes cannot see beyond the horizon of Earth's curve. Telescopes cannot glimpse farther than light has had time to travel. The universe, vast as it is, also carries this quiet rule. There are horizons, but they are not walls. They are the edges of knowledge, shaped by time itself. Astronomers speak of two major horizons that define what we can and cannot observe: the particle horizon and the event horizon. The first tells us how far light has been able to travel since the universe began. Because the cosmos has a finite age, only photons released within that span have reached us. Imagine standing in the middle of a growing sphere of visibility. Its surface marks the farthest distance from which any signal could possibly have arrived. That sphere, roughly 46 billion light-years in radius, is our observable universe. Beyond it, galaxies may exist, but their light is still on its way. We will see them only when time allows, if ever. The event horizon is subtler. It defines the outer boundary of what we will ever be able to observe. Space itself is expanding, and distant galaxies are carried outward with that flow. Some recede faster than light can bridge the gap, not because they move through space so quickly, but because the space between us and them continues to stretch. Their light, no matter how patiently it travels, will never arrive. They are not hidden by distance, they are hidden by time's expansion. The event horizon marks the limit of all future contact. These horizons reveal that the universe is both finite and unbounded. There is no cosmic wall where everything stops, yet there is a limit to what can be seen or reached. The boundary is not an object, but a condition. The intersection of light's constant speed and the universe's restless growth. It reminds us that knowledge always occupies a sphere within a larger unknown. On Earth, the idea of a horizon is comforting. Sailors once watched ships vanish over the curve of the sea, knowing they were not destroyed, only hidden by perspective. In the same way, the cosmic horizon invites wonder rather than fear. It tells us that there are things we cannot yet perceive, but that they still exist beyond the reach of sight. The unknown is not emptiness. It is potential waiting its turn. Scientists chart this invisible boundary with precision. Observations of background radiation, distant quasars, and the redshift of galaxies all help map the edge of our observable universe. Within that region, everything follows predictable laws. Beyond it, speculation begins. Yet even speculation has value. The act of imagining what lies past the horizon drives exploration and theory, expanding the boundaries of understanding even when evidence cannot yet follow. There is humility in realizing that the cosmos we see is only a portion of what exists. Our telescopes reveal billions of galaxies, each containing billions of stars, but that immense spectacle may represent just a fragment of the whole. The unseen beyond our horizon could hold structures and histories we will never witness, and still, they are part of the same continuous space that includes us. If you visualize the universe as a vast ocean, the horizon becomes a shifting line between what is illuminated and what remains in twilight. As time passes, that line moves. New light arrives. New regions become visible. The horizon expands, but it never disappears. The cosmos teaches this gentle lesson. Understanding grows, yet mystery always remains. So when you think of limits, do not imagine barriers. Imagine contours, curves of awareness shaped by time, light, and patience. The universe has no edges, only frontiers that move slowly outward like ripples across still water. Every discovery pushes that boundary farther, and every unanswered question keeps wonder alive. Within those horizons, there is already more than enough to fill a lifetime of looking up. When people first heard the phrase Big Bang, many imagined a grand explosion, a burst from some central point scattering matter into emptiness. But space did not erupt into something, it became something. The Big Bang was not an event that happened in space, it was the expansion of space itself. Every point in the universe moved away from every other, not through a surrounding void, but because the very fabric connecting them was stretching. To grasp this, picture a loaf of raisin bread as it rises in the oven. The dough expands, and each raisin drifts away from the rest, yet none of them occupy a special center. From the viewpoint of any raisin, the others appear to recede equally. The same happens in the cosmos. Galaxies do not rush outward from a single origin. They simply ride the growing fabric of space-time, carried apart like raisins in the dough of the universe. This truth first emerged from the observations of Edwin Hubble in the late 1920s. Measuring the light of distant galaxies, he discovered that their spectra were shifted toward the red end of the spectrum, a redshift, showing that the light waves had been stretched by the expansion of space during their journey. The farther a galaxy was, the greater its redshift, implying that space was expanding uniformly everywhere. Later, this observation became one of the strongest pieces of evidence for the Big Bang model. At first, scientists expected this expansion to slow under the pull of gravity, much like a ball thrown upward that eventually falls back. For decades, they debated whether the universe would one day contract again in a big crunch. But the discovery of distant supernovae in the late 20th century revealed something unexpected. Expansion is not slowing, it is accelerating. Some unseen form of energy, now called dark energy, appears to drive this acceleration, making the universe open wider as time goes on. Even though galaxies recede from one another, the distances within them do not change. Gravity binds stars, planets, and solar systems too tightly for spaces stretching to separate them. The expansion happens between clusters of galaxies, across the enormous voids that connect them. This subtlety often surprises people. The universe grows, but not everything inside it grows with it. Local gravity holds firm while the cosmic web as a whole drifts apart. From a philosophical view, this expansion changes how we think about infinity. There may be a finite amount of matter and energy, yet the reach of space itself can increase without limit. The universe does not expand into something else, it simply redefines the distance between points within itself. There is no outer edge and no center to travel toward. Every observer, no matter where they stand, sees the same pattern of retreat. If you could pause time and draw a grid across the universe, the lines of that grid would slowly stretch apart, while the dots representing galaxies remained fixed on them. With each passing billion years, light must travel farther to cross the same space. The consequence is a deep quietness. Distant galaxies grow dimmer, their light older and redder, until some drift beyond any possible observation. The visible universe gradually thins, leaving behind only local islands of stars. Yet this is not a story of loss. Expansion is the mechanism that allows the cosmos to remain dynamic, preventing collapse and making room for new generations of galaxies and stars. The same process that carries distant worlds away from view also keeps the night sky alive with constant renewal. As you imagine this motion, think of breathing, an inhale that never ends, a slow widening that has lasted since time began. The universe is not rushing outward in chaos, but unfolding with measured rhythm. You exist within that rhythm, held steady by gravity while space itself continues to stretch around you, patient and silent. In ordinary life, distance is simple. We measure in steps, in meters, or in miles. But when distances extend beyond planets and stars, ordinary rulers fail. To understand the scale of the universe, astronomers had to invent new methods, ways to measure across light years without ever leaving Earth. This work, patient and meticulous, turned the immeasurable into something the human mind could grasp. The first method is parallax, the same principle that helps your eyes perceive depth. Hold your thumb in front of you and alternate closing one eye, then the other. Your thumb appears to shift against the background. Astronomers use this shift to calculate how far a star lies. As Earth moves around the Sun, nearby stars seem to change position slightly against the more distant background. The amount of that shift, combined with the known size of Earth's orbit, allows precise measurement. For the closest stars, parallax provides the foundation for all further calculations, a first rung on the cosmic distance ladder. Beyond a few thousand light-years, parallax becomes too small to detect. Astronomers then rely on standard candles, objects whose true brightness is known. Certain types of variable stars, called Cepheids, pulsate regularly, and their pulsation period reveals their intrinsic luminosity. By comparing how bright they appear from Earth with how bright they truly are, scientists determine how far away they must be. Later, type Ia supernovae, massive stellar explosions of consistent brightness, extended this method to galaxies millions of light-years distant. Farther still, where even supernovae fade to invisibility, measurement depends on the redshift of light. Because the universe is expanding, the wavelength of light from distant galaxies is stretched during its travel, shifting toward the red end of the spectrum. The greater the redshift, the faster the galaxy is receding, and therefore the farther away it lies. This technique transforms color into distance, an elegant code written in light itself. Each of these methods overlaps the next, forming a ladder of verification. Parallax calibrates Cepheids, Cepheids calibrate supernovae, supernovae anchor redshift. Together they map the visible universe and reveal its scale with remarkable precision. What once seemed infinite now becomes chartable, not by direct touch, but by inference and patience. There is a quiet beauty in this approach. Science does not conquer distance through speed but through understanding. By measuring how light changes, we measure how space behaves. It is as if the universe speaks in variations of color and brightness, and astronomers have learned to listen. Modern technology continues to refine these measurements. The Gaia spacecraft, orbiting Earth, has mapped more than 1 billion stars with unprecedented accuracy, tracing the architecture of our galaxy in exquisite detail. Ground-based observatories and space telescopes extend the reach even farther, measuring light that has traveled for billions of years. Every improvement sharpens our image of the cosmos, but also deepens its mystery, for precision often reveals new questions hiding within the data. To measure the universe is also to measure ourselves. The effort shows the extraordinary reach of human curiosity, the desire to know what lies beyond direct sight. Yet it is done not through force, but through observation and patience, one calculation after another. This slow, careful process mirrors the rhythm of the cosmos itself, quiet, persistent, expanding by degrees. As you rest with this thought, picture the instruments pointed toward the night sky, mirrors catching light that began its journey before humans existed. Each photon carries a clue, each spectrum a sentence in the story of creation. The scientists who decode these signals work within silence, turning faint glimmers into knowledge. Their craft reminds us that the universe can be measured not by strength or speed, but by the steady discipline of looking and listening. In that patience, distance loses its power to intimidate. It becomes instead a gentle teacher, showing that understanding grows one wavelength at a time. When astronomers first measured how galaxies rotate, they expected to find predictable harmony. According to Newton's laws, Stars closer to the center should orbit faster, and those near the edge should move more slowly, just as planets in the solar system do, but the data refused to fit. Across galaxy after galaxy, outer stars were circling too quickly, as though something invisible were holding them in its gravitational grip. That mystery led to the concept of dark matter, a form of mass that neither emits nor absorbs light. It cannot be seen through any telescope, yet its presence is felt everywhere. In spiral galaxies, dark matter forms immense halos, extending far beyond the visible disk of stars. Without this unseen component, galaxies would fly apart. Their luminous matter alone does not provide enough gravity to keep them bound. The cosmos, it seems, is built on an invisible scaffold, evidence for dark matter multiplied. In galaxy clusters, astronomers observed gravitational lensing, light from distant objects bending more than visible matter could account for. They also detected the same gravitational signature in the early patterns of the cosmic microwave background. Each measurement pointed toward the same conclusion. Most of the universe's mass exists in a form we cannot directly detect. By current estimates, dark matter makes up about 27% of the total cosmic inventory, while the ordinary matter that forms stars, planets, and people contributes less than 5%. What, then, is this hidden substance? The answer remains one of modern physics' great enigmas. Some theories propose new particles, collectively called WIMPs, weakly interacting massive particles that rarely collide with normal matter. Others suggest lighter entities like axions, or even modifications to the laws of gravity at large scales. Experiments deep underground and in orbit continue to search for clues, listening for the faintest whispers of collision between visible and invisible matter. Yet the mystery itself holds a quiet beauty. The fact that so much of existence remains unseen reminds us that knowledge, though vast, is still incomplete. The visible cosmos, the stars, the nebulae, the glowing arcs of galaxies, is only a delicate frost on the surface of something far greater. Dark matter threads through the universe like an invisible lattice, shaping every luminous structure we can observe. It gathers galaxies into clusters and links those clusters into the vast cosmic web that fills all of space. This framework is not chaotic. It is ordered by gravity's simplest rule: mass attracts mass. Over billions of years, that attraction drew together the raw material for galaxies and stars, while the voids between them expanded. Without dark matter, the universe would have remained a uniform mist. The unseen gave form to the seen. In reflecting on this, it is natural to feel both humility and awe. We are creatures of the visible spectrum, yet our existence depends on what our eyes cannot detect. The same is true in life. Structures of meaning often rest upon foundations that remain invisible: trust, memory, gravity itself. Science, by naming and studying the unseen, transforms mystery into curiosity rather than fear. Imagine looking into the night sky and sensing not only the points of light but also the dark structure that binds them together. The stars trace its shape without revealing it, like lanterns strung along invisible threads. That unseen geometry is the quiet framework of everything. Dark matter's reality teaches a gentle lesson. Visibility is not the measure of importance. What holds the universe together and what holds people together often moves unseen, silent, and steady. In that realization lies comfort. The cosmos endures because its most essential forces do not need to shine to be real. If dark matter holds galaxies together, another invisible force does the opposite. It pushes them apart. This force is called dark energy, and it accounts for nearly 70% of everything that exists. It is not matter, nor light, nor any familiar form of energy, yet it shapes the universe more profoundly than all the stars combined. For decades, Astronomers assumed that cosmic expansion would gradually slow under gravity's pull. The universe might coast forever, or eventually collapse in on itself. Then, in the late 1990s, teams studying distant Type Ia supernovae discovered something astonishing. These exploding stars, used as standard candles to measure distance, appeared dimmer than expected. The only explanation was that space had expanded more than predicted, that expansion was accelerating, not slowing. That realization changed everything. It meant that the fabric of the cosmos contains a built-in form of energy that works against gravity, increasing with space itself. The more the universe expands, the stronger dark energy's influence becomes. Galaxies are not moving through a static void. The void itself is stretching faster and faster. Each cluster of matter drifts farther from the rest, carried by this silent, omnipresent force. Scientists describe dark energy mathematically through the cosmological constant, a term first introduced by Einstein. He added it reluctantly to keep the universe stable, later calling it his greatest mistake when expansion was discovered. Yet decades later, the concept returned as the simplest explanation for acceleration. Some physicists suspect that dark energy may be a property of vacuum energy, the faint quantum vibrations that fill empty space. Others imagine a changing field, evolving through time. Despite these ideas, no experiment has yet revealed its true nature. Unlike dark matter, which clumps and gathers, dark energy acts uniformly everywhere. It does not attract, it repels. It fills all of space evenly, as though emptiness itself contains pressure. The farther two regions of the universe are from each other, the more dark energy lies between them, pushing them apart. This quiet repulsion determines the ultimate fate of the cosmos. If it remains constant, galaxies will drift endlessly until most slip beyond one another's horizons. In that far future, each island of stars will float alone in darkness, surrounded by unreachable space. There is melancholy in that vision, yet also serenity. The same process that isolates galaxies ensures that the universe will never collapse into chaos. Expansion preserves order on grand scales, spreading energy thin, letting structures age gently rather than violently. The end of the universe, if one can call it that, will be neither explosion nor implosion, but a gradual quieting, a cooling into calm. Dark energy teaches that even the void is active. Emptiness is not absence, it is potential. What we perceive as nothing is full of subtle behavior, guiding the rhythm of cosmic time. To grasp this is to realize that the universe's stillness is an illusion. Beneath that stillness, everything is moving, driven by forces we cannot yet name. When you look at the night sky, imagine the faint tug of expansion at work between every point of light. Though imperceptible in the scale of a human lifetime, it defines the shape of the future. The stars do not simply drift, they are carried by a tide that never rests. The energy of space itself ensures that creation continues to unfold, that distance itself is alive. The universe is growing not because it must reach somewhere, but because it is, by nature, open. That openness is its quiet truth, a slow, endless widening in which everything moves apart yet remains part of one connected whole. If you could step outside the universe and look back upon it, you would not see a random scattering of galaxies. Instead, you would see a pattern, a vast, interlaced structure stretching across billions of light-years. This is the cosmic web, the grand architecture of matter shaped by gravity and time. From afar, it resembles the filaments of a delicate network, luminous threads woven through dark space, connecting immense clusters of galaxies like nodes in an endless net. The idea of this structure emerged from both observation and simulation. Early galaxy surveys in the 20th century revealed that galaxies are not distributed evenly. Instead, they form walls and filaments surrounding immense voids, regions nearly empty of matter. Later, Computer models tracing the growth of cosmic structure confirmed what the data hinted. Gravity, acting over billions of years, pulls matter into long strands while the spaces between them expand. What began as faint ripples in the density of the early universe has become a web of unimaginable size. Each filament in this web contains hundreds of millions of galaxies, bound together by dark matter halos. At the intersections of filaments lie colossal clusters where gravity is strongest, while the vast voids between them stretch for hundreds of millions of light-years. These voids are not truly empty. They contain a thin mist of gas and dark matter, so diffuse that it barely interacts with light. The pattern is both intricate and simple. Matter flows along invisible gravitational currents, forming bridges between the densest regions. The cosmic web shows that the universe, though seemingly chaotic, follows order on every scale. The same laws that guide the motion of planets also govern the shape of the largest structures. Gravity does not act randomly. It sculpts, slowly and persistently. Over time, galaxies migrate along filaments like rivers of light, merging and forming new systems at the junctions. The cosmic web is therefore not static but alive, continuously evolving as expansion stretches its threads and gravity pulls them taut again. Astronomers map this structure using massive sky surveys and gravitational lensing, where light from distant galaxies bends around unseen mass. By comparing observations with simulations, they can reconstruct the three-dimensional skeleton of the universe. These maps reveal a balance between emptiness and density, between stillness and motion. The cosmos, seen on its largest scale, resembles a living organism, a network of connections feeding energy and matter across vast distances. The resemblance to biological systems is more than poetic. Just as neurons form networks in a brain, galaxies form networks in space. Both rely on distributed connections, and both evolve through local interactions that generate global patterns. The cosmic web is not conscious, but it represents the same principle that nature favors everywhere: structure emerging from simplicity. When you look up at the night sky, it is easy to imagine stars as isolated points, scattered at random, yet every one of them is part of a far greater pattern, a filament stretching through the Milky Way, which itself lies along one strand of the web. Even the dark between stars is part of that structure, filled with the faint pull of unseen matter. The universe is not a collection of islands, it is a single continent of connected light. As you reflect on this, imagine the web as a quiet network that holds everything in gentle tension. Across its filaments, gravity hums softly, keeping order in motion. Through its voids, light travels freely, carrying messages between clusters. This is the universe seen not as explosion or chaos, but as harmony, an intricate balance of pull and release. In every direction, the same pattern repeats, reminding us that existence is unity disguised as distance. The cosmic web does not end anywhere. Its threads continue beyond what we can observe, interwoven with the unseen fabric of space-time itself, a timeless geometry binding everything that has ever been. The universe feels infinite, yet everything within it exists inside boundaries, natural limits defined not by walls but by conditions. These boundaries shape what can be known, measured, or experienced. Far from being obstacles, they give form to knowledge, carving clarity from immensity. Without them, everything would dissolve into sameness. One of the most profound boundaries is the speed of light. Nothing travels faster, and because of that limit, we can only receive information from regions whose light has had time to reach us. The edge of this visibility defines the observable universe. It is not an edge in space, but in time, a frontier beyond which the past is still unfolding, its light still on the way. In this sense, every boundary is a conversation between distance and duration, a rule set by the interplay of energy and expansion. Other limits exist on smaller scales. Stars live within thresholds of pressure and mass. Too small, and nuclear fusion never begins. Too large, and gravity collapses them into black holes. Planets orbit within zones of warmth. Step outside those zones, and oceans freeze or boil away. Even galaxies occupy regions of stability, held together by gravity yet torn apart if they grow too massive. Everywhere in the cosmos, order depends on balance. Scientists also recognize boundaries in what can be detected or described. Quantum mechanics, the study of the smallest scales, introduces uncertainty as a fundamental feature of reality. The position and momentum of a particle cannot both be known precisely. This is not a flaw in measurement, but a property of existence. On cosmic scales, relativity imposes its own limits. Mass warps spacetime, light follows curvature, and observers experience time differently depending on motion and gravity. Between the infinitely small and the infinitely large, we encounter not emptiness but law. Black holes embody these boundaries most vividly. At their event horizons, gravity becomes so intense that nothing, not even light, can escape. This is a literal horizon, a point of no return. Yet from outside, the black hole's surface appears calm, defined only by its mass, spin, and charge. Information about what falls in seems lost, but quantum theory hints that it might remain encoded subtly on the horizon itself. Even where physics meets its limits, patterns persist. The cosmos reminds us that boundaries do not end exploration, they invite refinement. Each limit leads to a deeper question, a more careful instrument, a clearer model. The edge of knowledge moves outward as understanding grows, just as the light from distant galaxies slowly expands the range of what we can see. Science is therefore not a quest to remove boundaries, but to understand them, to trace the outlines that give structure to reality. In a larger sense, boundaries are what allow meaning. A melody needs silence between its notes. A planet's orbit needs the restraint of gravity. Without limits, there could be no pattern, no continuity. The universe is infinite in extent but finite in possibility at any given moment. Its laws act as gentle constraints, ensuring that complexity unfolds gradually rather than all at once. As you rest with this thought, imagine the boundaries of existence not as fences but as contours, smooth gradients that define where one state becomes another. The same principle shapes our own lives: edges of perception, limits of understanding, thresholds of experience. To encounter them is not defeat, it is to stand at the frontier of what can be known. The universe is open yet disciplined, endless yet shaped. Its natural boundaries are not barriers placed against curiosity, but the frameworks that make curiosity meaningful. In their quiet precision, we find the language of balance, the understanding that even infinity requires form, and that every horizon, seen or unseen, is a promise of something more waiting just beyond it. All around the galaxy, within vast, cold clouds of gas and dust, the slow work of creation continues. These are stellar nurseries, the regions where stars are born. To the eye, through a telescope, they appear as faint veils or glowing nebulae, patches of luminous mist where gravity, chemistry, and time collaborate to turn darkness into light. The process begins quietly. Within a molecular cloud, tiny irregularities in density cause certain regions to pull slightly more strongly than others. Over millions of years, gravity amplifies these differences. Gas and dust drift inward, forming knots that grow denser and warmer. Eventually, the inward pull becomes unstoppable. As atoms collide more frequently, temperature rises to millions of degrees, and the core becomes a furnace of hydrogen fusion. A star is born. Fusion is nature's great alchemy. 4 hydrogen nuclei combine to make one helium nucleus, releasing energy as light and heat. This outward radiation pushes back against gravity, establishing a balance that allows the star to shine steadily for billions of years. In this equilibrium, Between collapse and expansion lies the quiet endurance of the cosmos. Different sizes of stars emerge from the same basic recipe. Small ones burn gently, consuming their fuel slowly and lasting for tens of billions of years. Massive ones burn fiercely and briefly, ending their lives in cataclysmic explosions that scatter heavy elements into space. These supernovae are not endings but beginnings. For the debris they cast off seeds the next generation of stars and planets. In this way, matter moves through cycles of collapse and renewal, ensuring that creation never truly stops. Our own sun was born about 4.6 billion years ago from such a process. Long before Earth existed, a previous generation of massive stars had enriched the local interstellar cloud with carbon, oxygen, and iron. When gravity gathered that cloud again, it carried within it the ashes of older stars, the raw material from which planets, oceans, and living beings would eventually form. Every atom in your body heavier than hydrogen was forged in the heart of a star. You are, in the most literal sense, made of stardust. Astronomers study young stellar regions like the Orion Nebula or the Eagle Nebula to witness this ongoing transformation. Inside them, new suns ignite within cocoons of gas, sometimes accompanied by swirling disks of material that may one day become planets. Jets of plasma shoot outward from their poles, carving tunnels through the surrounding cloud, announcing birth through motion and light. Star formation is both violent and graceful, energy concentrated into form, chaos finding rhythm. The forces that create destruction elsewhere in the universe serve here as architects, sculpting balance from gravity and heat. Each star that emerges becomes a lighthouse in the cosmic night, illuminating dust and nebulae, revealing the structure from which it came. Over time, clusters of young stars drift apart, and their parent clouds disperse into the galactic background. The cycle resets. New clouds condense, new stars flare to life, and the pattern continues, written across billions of years. In this continuity lies reassurance. The universe does not simply exist, it renews itself. If you could watch the galaxy in accelerated motion, you would see waves of creation sweeping through it, light blooming where once there was only shadow. Every sunrise on Earth echoes that same story. Hydrogen becoming helium, light emerging from gravity's grip. As you think of this process, imagine the quiet perseverance behind it. No sudden miracle, no instant creation, just the patient rhythm of physics, repeating endlessly. Stars are born not through command but through balance, each a reminder that brilliance arises from steady pressure and time. The night sky is not a decoration. It is a record of birth written in light, each star a sentence in the universe's ongoing autobiography. In the same cosmos that gives birth to stars, there also exist places where light itself disappears. These are black holes, the most extreme expressions of gravity known. They are not objects in the usual sense, but regions where matter has been compressed beyond any imaginable density, curving space-time so sharply that nothing, not even light, can escape. Most black holes form when massive stars die. After burning through their nuclear fuel, they lose the outward pressure that held gravity in balance. The core collapses inward with unstoppable force, crushing atoms into a singularity, a point where the laws of physics, as currently known, break down. Around this singularity lies the event horizon, the invisible boundary separating the inside from the outside universe. Once anything crosses it, there is no return. All paths lead inward. From afar, however, the black hole appears perfectly smooth, defined only by three measurable qualities: mass, spin, and electric charge. The region surrounding a black hole is anything but empty. Matter falling toward it forms an accretion disk, a spiraling torrent of gas heated to millions of degrees. Friction within this disk releases immense energy, making it one of the brightest phenomena in the universe. Paradoxically, the presence of something that allows no light gives rise to some of the most brilliant emissions ever observed. Jets of charged particles can stream from the poles at nearly the speed of light, powered by magnetic fields twisting around the hole's rotation. Black holes vary in size. Some are only a few times the mass of the Sun, while others, supermassive black holes, weigh billions of solar masses and sit at the centers of galaxies. The one in our own Milky Way, called Sagittarius A*, quietly governs the orbits of nearby stars. Through decades of observation, astronomers have confirmed its existence by tracking those orbits, which move with extraordinary speed around an unseen point. In 2019, an international collaboration captured the first image of a black hole's shadow, a dark circle surrounded by a glowing ring, the light of the accretion disk distorted by gravity itself. Despite their reputation as destroyers, black holes also act as stabilizers. Their gravitational influence organizes galaxies, and their violent outbursts regulate star formation by dispersing gas and dust. In this way, they serve as both creators and gatekeepers, shaping the universe from within its deepest darkness. Theoretical physicists continue to wrestle with the paradoxes black holes present. According to quantum theory, information about matter cannot be destroyed, yet anything that falls into a black hole seems lost forever. Some suspect that this information is preserved in subtle vibrations on the event horizon, a concept known as the holographic principle. Others explore whether black holes might one day evaporate through slow radiation, a prediction made by Stephen Hawking. Such radiation, if real, would cause even the most massive black holes to fade eventually, returning their energy to the cosmos. To contemplate a black hole is to confront the limits of understanding. These entities are nature's test cases for the deepest laws of reality, where relativity and quantum mechanics meet and challenge each other. They remind us that knowledge always edges up against mystery. Yet the mystery is not empty, it is fertile, inspiring inquiry that may one day unify the great theories of physics. As you think of these invisible giants, imagine not destruction but balance. Gravity pulls inward, while energy radiates outward. Matter collapses, but information may endure. In the universe's grand equation, even darkness serves a purpose. Black holes are not the end of space. They are part of its rhythm, the deep bass notes that give the cosmic symphony depth. Among all the mysteries of the universe, one question follows every movement, every change. Why does time flow in one direction? The laws of physics work equally well forward or backward, yet our experience insists that the past is fixed and the future remains open. This directionality, the arrow of time, arises from a single, universal principle: entropy, the natural tendency of systems to move from order toward disorder. Entropy can be understood through simple examples. A drop of ink spreading through water never unmixes itself. A shattered glass does not leap together again. Heat flows from warm to cold, but never spontaneously the other way. In each case, there are far more ways for matter to be disordered than arranged. That imbalance defines time's one-way motion. The universe itself began in an extraordinarily ordered state, with matter and energy evenly distributed, but gravitational potential low. From that improbable smoothness, structure has grown. Stars, planets, galaxies, all formed as entropy increased. The very act of creation, paradoxically, moves forward through increasing disorder. On cosmic scales, this process gives the universe its narrative. Each star that shines converts hydrogen into heavier elements, releasing energy and spreading it outward. That radiation cannot be recollected. It diffuses into space, increasing entropy. The steady expansion of the cosmos stretches light to longer wavelengths, thinning its energy further. Step by step, the universe evolves toward equilibrium, a condition in which all gradients, all differences, have evened out. This distant state is sometimes called the heat death, when energy becomes too evenly distributed to do work. But that far future, measured in unimaginable trillions of years, also carries calm, a resting point, not an ending. Time's arrow is visible everywhere, from the motion of galaxies to the beat of a human heart. Each heartbeat is a conversion of energy, a small increase in entropy that marks another irreversible step forward. Memory, too, follows this rule. We remember the past because it left traces, physical imprints on the brain and in the world, but the future leaves none. Causality flows from lower to higher entropy. We experience its passage as the feeling of before and after. Even at the smallest scales, the arrow of time emerges statistically. The fundamental laws are reversible, but when trillions of particles interact, probabilities dominate. The universe could, in theory, reverse itself perfectly, but the odds are so infinitesimal that the event might as well be impossible. Time's direction is not imposed from outside, it arises naturally from the way complexity behaves. Scientists sometimes describe entropy as the measure of information missing about a system. From that perspective, time is a story of information dispersing. Stars burn, matter decays, and complexity transforms, not because the universe prefers disorder, but because it explores every possible configuration. The increase of entropy is simply the expansion of possibility. Yet this progression is not bleak. It allows transformation. A star's death enriches space with elements that form planets and life. Each irreversible event becomes the foundation for something new. The arrow of time ensures that the universe does not loop endlessly in repetition but continues to create. Its forward motion is the heartbeat of change itself. When you consider time flowing one way, imagine it not as a river rushing past, but as a gentle unfolding. Every second that passes adds to the universe's record, inscribed in radiation, matter, and memory. The future is not a destination waiting ahead. It is the continuous opening of potential, born from the irreversible act of existing now. As you rest, feel how this same direction runs through everything: growth, decay, learning, forgetting. The arrow of time moves quietly through all forms, carrying creation forward one breath at a time. It does not hurry. It does not pause. It simply flows, giving structure to the infinite and turning motion into meaning. When we speak of the universe, we usually mean everything that exists: space, time, matter, and energy combined into one continuous whole. Yet some physicists and cosmologists have asked a daring question: what if our universe is only one of many? This idea, known as the multiverse, is not fantasy but an attempt to explain patterns we observe in physics and cosmology that seem too finely tuned to be coincidence. The roots of this concept lie in cosmic inflation, the theory that right after the Big Bang, space expanded at a breathtaking rate, faster than light could cross it. That brief, explosive growth smoothed the universe and set the stage for galaxies to form. Some versions of inflation suggest that it never ended everywhere at once. Instead, expansion continues in distant regions, creating endless bubble universes, each with its own local laws of physics. In this vision, the cosmos is like a vast ocean of space-time foam, where each bubble is a separate universe, sealed from the rest. Our own universe could be one such bubble, born from a small fluctuation in a larger inflating field. Inside it, the Big Bang would appear as a beginning. Outside, the greater expansion continues indefinitely. If this is true, space itself has no final boundary, only regions with different histories and perhaps even different forms of matter. Some universes might have more dimensions, others slightly altered constants of nature, Most would be sterile, but a few could resemble ours, hospitable to stars and life. Another version of the multiverse emerges from quantum mechanics, specifically the many worlds interpretation. In that view, every quantum event, every moment when a particle could take multiple paths, actually realizes all possibilities. Each outcome branches into a new version of reality, parallel to the others. These universes would not be far away in space, but layered in possibility, each as real as the one we know, differing by the smallest of decisions, a photon's spin, a coin's fall, a thought's direction. Such ideas sound speculative, and they are. The multiverse cannot yet be observed directly. Each bubble or branch lies beyond any conceivable horizon. No signal can cross between them. But mathematical consistency and certain patterns in cosmic radiation lend subtle hints that the universe may indeed be part of something larger. In some inflation models, the shape of the sky, the tiny fluctuations in the cosmic microwave background, could bear traces of collisions with neighboring bubbles long ago. Scientists continue to search for such signatures, knowing that even indirect evidence would profoundly alter our understanding of reality. Philosophically, the multiverse raises profound questions. If countless universes exist, then every possible version of events might unfold somewhere. The constants that make life possible here would not require a grand design, only probability across infinite trials. Our universe would be one of the few where conditions align by chance to allow complexity and consciousness. Yet this vast perspective can bring not alienation but humility. It reminds us that existence is not limited to our perception. The laws that govern our world could be one variation among many, yet we still have the privilege of observing and understanding them. Whether or not other universes exist, contemplating them stretches the human mind beyond habit and scale. If you imagine this possibility, picture an endless ocean, each ripple a separate cosmos expanding in silence. No bubble knows the others, yet all share the same underlying sea of energy and law. Our universe floats among them, fragile yet luminous, one expression of infinite potential. The multiverse, real or not, reflects humanity's deepest impulse to push thought beyond boundaries. It does not replace wonder, it expands it. Even if our universe stands alone, the fact that it can contain the idea of others shows how boundless imagination has become, a mirror of the infinity it seeks to describe. When we imagine space, we often picture it as flat, an invisible grid that stretches endlessly in every direction. Yet geometry, when applied to the universe itself, tells a subtler story. The cosmos may be flat, curved, or something stranger still. Understanding that shape means discovering how space bends under the influence of gravity and energy, revealing that even emptiness possesses structure. Einstein's general theory of relativity transformed how we see geometry. It showed that mass and energy curve space-time, and that curvature dictates the motion of everything within it. Light follows those curves just as planets do. To visualize this, think of a sheet of fabric stretched tight. A heavy ball placed on it creates a depression, and smaller balls roll toward it, not because they are pulled, but because the surface itself is bent. Space behaves the same way, only in 4 dimensions, 3 of space and 1 of time. On cosmic scales, the curvature of the universe depends on its overall density of matter and energy. If that density is high enough, space folds back on itself like the surface of a sphere. A traveler moving straight ahead would eventually return to the starting point, never encountering an edge. If the density is too low, space curves outward like a saddle, expanding forever and never looping back. Between those extremes lies a perfectly balanced case, a flat universe, where parallel lines remain parallel indefinitely. For decades, astronomers sought to measure which shape describes reality. They looked to the cosmic microwave background, the afterglow of the Big Bang, for answers. Tiny fluctuations in that ancient light act as markers, revealing how space stretches between us and the early universe. By analyzing the patterns of those fluctuations, scientists determined that our universe is astonishingly close to flat. The angles of cosmic triangles add up almost exactly as they do on a tabletop. But flat here does not mean simple or featureless. It means that the geometry of the cosmos, on average, is perfectly balanced between contraction and expansion. Even within this near flatness, space can contain complex topology, its own form of hidden architecture. Just as a two-dimensional surface can be wrapped into a torus or a Mobius strip, three-dimensional space might loop back on itself in ways that defy direct perception. Light could travel in circles vast enough that a distant galaxy might one day appear again from another direction, its image arriving from different epochs. The universe could, in theory, be both finite and unbounded, limited in volume, yet without any outer surface. Such ideas blur the distinction between geometry and existence. The shape of space is not just a stage upon which events occur, it is part of the story itself. The universe does not sit inside anything, it is the structure. Galaxies drift not through emptiness but along the curves of spacetime, their paths determined by the invisible geometry beneath them. This realization has changed how scientists and philosophers think about the word nothing. Empty space is not void but field, a medium with measurable properties, able to expand, ripple, and bend. Its geometry carries energy, and that energy, in turn, shapes its geometry. The dance between form and force continues endlessly, producing a cosmos that builds itself from its own curvature. As you picture this, imagine not a flat plane or a hollow sphere, but a flexible continuum, something that can fold, stretch, and twist without ever tearing. In this view, space is alive with structure even where matter is sparse, a silent architecture connecting every star to every particle. The geometry of the universe is the quiet handwriting of reality itself, invisible, continuous, and without edge, shaping the path of every photon that has ever traveled through it. Infinity is one of the simplest ideas to imagine, and one of the hardest to truly understand. We use the word easily to describe what has no end, yet in mathematics infinity is not a single concept, but a family of ideas, each with its own texture and size. Exploring it offers a bridge between logic and wonder, showing how the mind reaches toward what the universe seems to embody. The simplest kind of infinity is the countable one. If you can list its elements, like the sequence of natural numbers 1, 2, 3, and so on, it is infinite, yet orderly. No matter how far you count, there is always another number waiting. This infinity feels familiar, like a road stretching endlessly ahead, but mathematicians discovered that not all infinities are equal. The set of real numbers, for instance, all the decimals filling the spaces between integers, is larger in a fundamental way. You could never list them all, even with infinite time. This is uncountable infinity, a deeper level of endlessness. Between any 2 points, however close, there lies an unbroken continuum of possibilities. The discovery that infinities come in different sizes was revolutionary. It showed that the limitless itself can be measured, compared, and structured. This insight, first formalized by the mathematician Georg Cantor in the 19th century, revealed that mathematics could describe the infinite not as chaos but as hierarchy, a layered system in which even boundlessness obeys laws. The physical universe echoes this logic. Space and time, though vast, appear continuous. Between galaxies or between moments, there are no gaps small enough to stop the flow. Yet modern physics also hints that the continuum may eventually dissolve into discreteness, that space itself could be quantized into unimaginably tiny units called Planck lengths. Infinity, then, may not describe the literal architecture of the cosmos, but rather the limit of what our equations can express. It is the horizon of mathematics, just as the speed of light is the horizon of motion. For cosmologists, infinity raises difficult questions. Is the universe truly infinite, extending forever in all directions, or merely unbounded, curving back on itself so that travel never ends but space itself remains finite? Current evidence suggests a near-flat geometry, compatible with both possibilities. If space is infinite, then every arrangement of matter could repeat somewhere, simply because all patterns occur infinitely often. If finite, its limits may loop so widely that they can never be reached. Philosophically, infinity plays a quiet role in human thought. It represents aspiration, the desire to extend beyond the immediate and the measurable. Ancient philosophers associated it with perfection. Modern science treats it as a useful approximation. We speak of infinite density at a singularity or infinite expansion at the edge of time, but these terms signal where our understanding stops. Infinity marks the boundary between knowledge and imagination. In daily life, we encounter gentle reflections of it everywhere: the branching of trees, the recursion of coastlines, the self-similarity of snowflakes. Each hints at a pattern that could continue without end if nature had limitless scale. The universe, through mathematics, seems to whisper the same refrain: no matter how finely you divide, there is always more detail waiting beneath. To rest in the thought of infinity is not to be lost in it, but to accept its calm logic. It assures us that the mind can touch what it cannot contain. The infinite, whether real or conceptual, teaches humility. There will always be another step, another number, another horizon beyond the one we reach. As you think of this, imagine a simple line stretching away until sight dissolves. That line is both finite and infinite. It can be measured locally but has no ultimate end. Infinity begins wherever we stop counting. In its quiet way, it invites patience, reminding us that curiosity itself is an unending journey, one that mirrors the boundless universe it seeks to understand. When we picture galaxies, we often imagine great spirals like the Milky Way, vast disks of stars, bright and majestic. Yet most galaxies are nothing like that. The majority are faint, small, and easily overlooked. Clouds of starlight so diffuse that they vanish against the darkness. They are the quiet citizens of the cosmos, holding as much history as their luminous cousins but speaking in whispers instead of flares. Astronomers call them dwarf galaxies, and they outnumber the bright spirals by a wide margin. Some contain only a few million stars, tiny compared to the hundreds of billions in the Milky Way. Others are even fainter, ultra-diffuse galaxies that stretch as wide as our own but contain only a fraction of the light. For centuries they remained invisible, hidden by their faintness, until digital detectors and long exposures began to reveal them as ghostly smudges around larger galaxies. These dim systems are not trivial. They are the building blocks of cosmic structure. In the early universe, small clumps of matter formed first, merging over time into larger systems. Many dwarf galaxies still preserve that ancient state, untouched relics from the dawn of galaxy formation. Studying them allows scientists to glimpse how the first structures assembled from the primordial mix of gas and dark matter. Dark matter plays a starring role here. The motions of stars within these faint galaxies show that most of their mass is invisible. Without dark matter's gravitational anchor, their sparse stars would drift apart. In this sense, dwarfs act as laboratories for understanding the unseen framework of the cosmos. By observing how their stars move, astronomers can test theories about the behavior of dark matter itself. These galaxies also hold clues to the chemical evolution of the universe. Because they are small and isolated, each develops its own distinct history of star formation. Some stopped making stars billions of years ago, frozen fossils of the early cosmos. Others continue quietly, producing a few new suns each century. Their chemical makeup records the sequence of generations that lived and died within them, each new star inheriting elements forged by those before. In their simplicity, they preserve the fingerprints of cosmic evolution with remarkable clarity. From a distance, faint galaxies are nearly transparent. Their stars spread so thinly that space seems to shine through them. Yet, they are resilient. They orbit larger galaxies like satellites, sometimes torn apart by tidal forces, their stars scattered into streams that trace their vanished paths. These stellar rivers, winding through the halos of major galaxies, are the silent remnants of countless dwarfs absorbed over time. Even our Milky Way is ringed by such streams, evidence of a long history of cosmic merging and renewal. The faintest galaxies challenge not only instruments but imagination. Their discovery reminds us that brightness is not the same as significance. What matters most in the structure of the universe often hides beneath visibility. The unseen and the subtle carry the greatest weight, just as dark matter outweighs light, and gravity shapes what illumination only reveals. There is poetry in their persistence. Long after the bright cores of galaxies have faded, many dwarfs will remain, their low fuel consumption granting them lifespans beyond the universe's current age. They endure not through brilliance but through economy, conserving their energy quietly in the darkness. As you picture them, think of these faint galaxies as the punctuation marks between cosmic sentences, small, steady, and essential to the rhythm of the whole. Their dim light still travels across time, whispering of beginnings when the cosmos was young. They remind us that the universe's story is not written only in the glow of grandeur, but also in the endurance of the unseen, the gentle constancy that keeps everything connected long after the brightest lights have gone out. Between the galaxies lies what seems, at first glance, to be nothing. The night sky's darkness suggests vast emptiness, a vacuum stretching endlessly from one cluster of stars to another. But space is never truly empty. The intergalactic medium, or IGM, fills the regions between galaxies, a near-invisible substance so thin that a cubic meter contains only a few atoms, yet it plays a crucial role in the life of the universe. To imagine the IGM, think of a faint haze that pervades all of space. Most of it is hydrogen and helium, the simplest elements forged during the Big Bang. Over billions of years, stars and galaxies have enriched this haze with traces of heavier elements, carbon, oxygen, iron, blown outward by supernovae and galactic winds. Every galaxy both draws material from this medium and gives material back to it, in a slow exchange that connects everything in a vast, cosmic circulation. Detecting something so diffuse is a challenge. It cannot be seen directly through telescopes because it emits little or no visible light. Instead, astronomers observe it indirectly through the absorption lines it leaves on the light of distant quasars, brilliant galaxies powered by supermassive black holes. As quasar light travels toward us, it passes through clouds of intergalactic gas. Each cloud absorbs a specific wavelength, leaving a faint signature on the spectrum. By studying these fingerprints, scientists map the structure and composition of matter spread across billions of light years. These observations reveal that the intergalactic medium is not uniform. It forms filaments and sheets that trace the same cosmic web connecting galaxies. Within these filaments, matter slowly flows toward denser regions, feeding the growth of clusters while the voids between them expand. The IGM, though ghostly thin, holds more baryonic matter, the ordinary atoms that make up visible objects, than all the stars in the universe combined. It is the ocean in which galaxies drift, like islands. Temperature varies dramatically across this medium. In the deep voids, gas remains cold, only a few degrees above absolute zero. In denser regions near galaxies, shock waves and radiation heat the gas to millions of degrees, creating what astronomers call the warm-hot intergalactic medium, or WIM. Detecting this warm component has been a major goal of recent research, since it may contain much of the universe's missing ordinary matter, the matter inferred from theory but unaccounted for in direct observation. The intergalactic medium also carries the faint imprint of magnetic fields, relics from the early universe that have stretched and evolved with cosmic expansion. These fields guide the motion of charged particles and may influence how galaxies form and rotate. Even here, in the loneliest reaches of space, order persists. Though the IGM appears inert, it is dynamic over cosmic time. Streams of gas fall into galaxies, replenishing them with the raw material for new stars. In turn, stellar explosions and galactic winds return enriched gas to intergalactic space, creating a grand, slow recycling system. The boundary between galaxy and medium is therefore porous, a region of exchange rather than separation. Thinking of this invisible ocean alters our view of the universe. What we see, the bright points of galaxies and clusters, is only the froth upon an underlying tide of matter. The space between is not emptiness but continuity, the connective tissue of the cosmos. Without it, galaxies would be isolated systems, deprived of nourishment and interaction. With it, they belong to a single living network. As you reflect on this, picture the intergalactic medium not as a void but as a quiet reservoir, vast and patient. Within it, every atom drifts in slow motion, waiting perhaps billions of years to join a star, a planet, or a living being. The universe breathes through this medium, exhaling matter and drawing it in again. The darkness between galaxies is not lifeless space. It is the silence in which creation pauses, gathering strength for the next act of formation. For centuries, gravity was understood as a force that pulled objects toward one another. Planets circled the sun, apples fell to the ground, and invisible attraction seemed to bind everything in the cosmos. But Einstein's theory of general relativity revealed something deeper. Gravity is not a pull but the shape of spacetime itself. When massive objects move or collide, that shape ripples, sending waves outward across the universe, gravitational waves. These waves are extraordinarily faint. By the time they reach Earth, they stretch and compress space by less than the width of a proton. Yet they carry information from some of the most violent events imaginable: merging black holes, colliding neutron stars, and perhaps even the echoes of the Big Bang itself. The first hint that gravitational waves truly existed came from a binary star system discovered in the 1970 seconds, a pair of neutron stars orbiting each other with astonishing speed. Over time, astronomers noticed that their orbit was shrinking precisely as relativity predicted. If they were losing energy through invisible ripples in space-time. It was indirect proof, but persuasive. Decades later, humanity built instruments capable of detecting those ripples directly. The Laser Interferometer Gravitational Wave Observatory, LIGO, achieved what once seemed impossible. Its detectors, long vacuum tunnels several kilometers in length, use lasers to measure minute changes in distance between suspended mirrors. When a gravitational wave passes through Earth, it slightly distorts space, changing the relative length of those tunnels by an infinitesimal amount. In 2015, LIGO recorded such a signal. Two black holes, over 1 billion light-years away, had merged into one, sending a pulse of curved space-time across the cosmos. For the first time, humanity had heard the universe rather than merely seen it. Since that moment, dozens of gravitational wave events have been detected. Each carries a unique signature, the mass, distance, and spin of the merging objects encoded in the wave's tone. These signals open a new kind of astronomy. Unlike light, gravitational waves are not blocked or scattered. They pass unimpeded through dust, gas, and even entire galaxies. They allow scientists to observe cosmic regions that would otherwise remain forever hidden behind light's limitations. Gravitational wave astronomy has already begun to transform understanding. The detection of a neutron-star collision in 2017 produced both gravitational and electromagnetic signals, linking the two kinds of observation for the first time. That single event confirmed that such mergers forge heavy elements like gold and platinum, scattering them into space to seed future planets. It also provided new ways to measure cosmic expansion, refining the value of the Hubble constant. Beyond observation, these ripples hold profound philosophical meaning. They demonstrate that space-time itself is flexible, responsive, a living fabric rather than a static backdrop. Every motion, every collision, leaves a trace that continues outward forever, altering the geometry of existence by the smallest imaginable degree. The universe is not silent, but full of vibration, a cosmic resonance that never fully fades. Someday, detectors may become sensitive enough to record the faint gravitational murmurs left over from the universe's first moments, echoes of the inflationary expansion that began everything. Listening to those waves would be like hearing the universe's birth cry, a vibration older than any light. As you think of this, imagine space not as still emptiness but as water, its surface trembling with subtle ripples from distant events. These waves pass through you even now, expanding and contracting your atoms ever so slightly. You do not feel them, but they connect you to every movement that has ever occurred, from colliding stars to the turning of galaxies. The discovery of gravitational waves reminds us that perception can always deepen. What once seemed absolute stillness turns out to be alive with rhythm. Even the void hums softly with memory, and the universe itself becomes music, the slow, patient song of space and time, resonating forever. The story of the universe can be told as a single, continuous timeline, an unfolding from simplicity to complexity, from darkness to light. Each chapter lasts billions of years, yet together they form a coherent sequence that reveals how everything we know, from galaxies to life, emerged from the same initial spark. It begins with the Big Bang, not an explosion in space, but an expansion of space itself. Time, matter, and energy appeared together, contained in a searing, dense state. Within the first second, the universe grew unimaginably, cooling just enough for fundamental forces to separate: gravity, electromagnetism, and the nuclear forces that govern atoms. Protons and neutrons formed, and after a few minutes, simple nuclei of hydrogen and helium appeared. The cosmos, though still glowing, had begun to take shape. For hundreds of thousands of years, the universe remained opaque, filled with hot plasma. Then, as it cooled, atoms formed, allowing light to travel freely. That light became the cosmic microwave background, still visible today as a faint, ancient glow. The next long era was quiet, a cosmic dark age when no stars yet shone. Matter gathered slowly under gravity, forming dense clouds that would one day ignite. After several 100 million years, the first stars flared into being, ending the darkness. Their intense radiation transformed the universe, reionizing hydrogen and lighting the cosmos anew. These first stars were massive and short-lived, fusing heavier elements before exploding as supernovae. Their deaths enriched surrounding gas with carbon, oxygen, and iron, the raw materials for future generations of stars and, eventually, for life. Galaxies began to assemble as gravity pulled stars together. Over billions of years, they merged and evolved into the spirals and ellipticals we see today. Around 9 billion years after the Big Bang, in one ordinary arm of the Milky Way, a new star formed, our Sun. From the leftover dust of its birth, planets condensed, including Earth, a small, rocky world with the right conditions for liquid water. Life on Earth appeared quickly, within a few 100 million years of the planet's formation. Simple cells arose first, then more complex organisms. Over time, evolution produced plants, animals, and eventually, consciousness, beings capable of looking back at the universe and asking how it came to be. In that sense, the cosmic timeline folds in on itself. Matter that once drifted as hydrogen gas now thinks, dreams, and studies its own origins. The timeline also looks forward. Stars continue to burn hydrogen into helium, galaxies continue to move apart, and the expansion of the universe accelerates under dark energy. In the far future, the Milky Way and the Andromeda Galaxy will merge, forming a new, larger system. Billions of years beyond that, stars will exhaust their fuel, and the night sky will slowly fade as galaxies drift beyond sight. This progression, from fire to structure, from structure to awareness, shows that time is not merely a sequence of moments but a process of transformation. Each stage contains the seeds of the next. The universe does not rush, it unfolds. To visualize it, imagine a long ribbon stretching from your fingertips to the horizon. Every millimeter represents millions of years. Along that ribbon, the first stars appear almost at the beginning, the sun halfway along, and humanity only at the very tip. The immensity of the past is humbling, yet it also connects us to everything that preceded us. We are part of the same continuum that began with the first expansion of space. As you reflect on this timeline, think of it not as distant history but as an ongoing rhythm. The atoms within you once shone in ancient stars and will one day return to them again. The story of the universe is not finished. It continues every moment, written in light, motion, and time itself, carrying forward without pause toward whatever new forms await beyond our horizon. Human curiosity has always reached beyond the visible, but every era of discovery brings us face to face with a new boundary, the limit of what instruments can perceive. In the universe, these edges of detection shift constantly as technology and imagination advance. Yet no matter how powerful our telescopes become, there will always remain a horizon beyond which light has not arrived, a silence beyond the reach of even our most sensitive instruments. The first explorers of the sky used little more than glass lenses and patience. Galileo's telescope revealed moons around Jupiter and craters on the moon, discoveries that expanded humanity's vision tenfold. Today, space-based observatories extend that reach 1 trillion times farther, detecting light from galaxies born less than 1 billion years after the Big Bang. The modern quest to detect the faintest signals is an extension of that same instinct, to make the unseen known. At the farthest frontier lies the cosmic microwave background, the oldest light we can detect. Beyond it, the universe becomes opaque. Photons from earlier times cannot reach us. In that sense, even the most advanced telescope faces an intrinsic wall, not a physical barrier, but a temporal one. To see further into the past, we must invent new forms of observation, ways to sense what existed before light could travel freely. Gravitational waves, neutrinos, and the subtle patterns imprinted on matter itself are among the tools scientists now use to probe that hidden epoch. Closer to home, edges of detection appear in subtler ways. Astronomers hunt for planets around distant stars by measuring the faintest dips in brightness as a world passes in front of its sun. These variations are often smaller than a fraction of 1%, tiny flickers that require exquisite precision. Others search for the signatures of life in the form of atmospheric gases or thermal patterns, signals so faint they blur into noise. Each new discovery depends on pushing detection just beyond its previous boundary, turning whispers into data. The struggle against noise is constant. Every observation is a dialogue between signal and interference, between the message the universe sends and the distortions of atmosphere, electronics, and human error. That balance demands patience. A single image from a deep space telescope can require weeks of exposure, collecting photons one by one from galaxies billions of light years away. It is a form of listening, slow and deliberate, in which understanding accumulates grain by grain, Even when instruments reach their physical limits, theory extends perception further. Scientists model what cannot yet be seen, predicting signals that future technology might confirm. Each generation builds on the imagination of the previous one. In this way, progress does not erase boundaries, it moves them. The edge of detection becomes a moving frontier, always ahead, always just out of reach. There is something profoundly human about this endless pursuit. Our eyes evolve to see a narrow band of light, yet we have taught ourselves to perceive far beyond it. Radio waves, infrared heat, X-rays, and gamma rays. We have turned the universe into an orchestra of frequencies, each carrying a different piece of its story. What began as simple stargazing has become a dialogue across space and time. The edges of detection remind us that ignorance is not a flaw but an invitation. Each limitation defines where discovery begins. The faintest signal, once captured, changes the map of understanding forever, and beyond that new map waits the next silence, ready to be explored. As you think of these boundaries, imagine the universe as a vast sea of information. Our telescopes are small vessels, their antennas and mirrors, the sails catching the faintest winds of light. The horizon may retreat as we approach, but that does not diminish the journey. It ensures that curiosity will never end. The cosmos is generous with mystery, and each boundary we touch is a reminder that even silence can be full of meaning. The universe is in constant motion. Galaxies drift apart, stars spin, atoms vibrate. Yet within this grand choreography, there are also pauses, intervals of calm where forces balance and change slows almost to stillness. These are the moments of rest that give structure to the cosmic rhythm, the silent measures between crescendos. Without them, the universe would be all motion and no meaning. One such pause lies in the long, steady life of a star. After the turmoil of its birth, a star spends billions of years in quiet equilibrium, its inward pull of gravity perfectly matched by the outward pressure of fusion. Our Sun has been in that stable phase for nearly 5 billion years and will remain there for several billion more. In its calm glow, planets follow gentle orbits, and life has time to unfold. That serenity, the product of balanced forces, is the cosmic equivalent of a held breath, motion without upheaval. Rest also occurs on greater scales. Galaxies, once wild with collisions in the early universe, now rotate in relative peace, their stars tracing graceful spirals for hundreds of millions of years. Between bursts of creation, they settle into long, quiet intervals. Even the vast voids separating clusters are forms of rest, regions where gravity has already done its work, leaving behind a stable emptiness that expands slowly, evenly, without turbulence. There are smaller pauses, too, woven through every system. The motion of a pendulum, the orbit of a moon, the oscillation of an atom, all pass through moments when speed reaches zero before direction reverses. These instants of stillness are brief but fundamental. Without them, motion could not exist. They are the punctuation marks in nature's sentences, giving rhythm to its flow. Even the universe itself has experienced its own resting phases. After the violent birth of stars and galaxies, there followed ages of slow evolution. The current era, when expansion continues smoothly and dark energy dominates, is one of relative quiet compared to the fiery past. The universe breathes between acts, waiting for new structures to emerge in distant epochs. In its vast timeline, eons of calm are as important as the brief flares of transformation. Moments of rest are not empty, they are full of potential. In physics, equilibrium is never absolute. Beneath apparent stillness, particles continue to vibrate, fields fluctuate, and energy hums quietly. Absolute silence does not exist, only balance so perfect that motion cancels itself. This subtle activity, hidden beneath calm, is what allows renewal to begin again. The sun's quiet radiance sustains life because its inner reactions proceed steadily, without interruption. Stillness, paradoxically, is what keeps everything alive. In human terms, rest holds similar importance. We live in a universe of constant flux, seasons changing, atoms rearranging, thoughts emerging and fading. Yet between those moments, there are intervals where everything aligns. The steady rhythm of a heartbeat, the pause between breaths, the silence after understanding. These pauses mirror the cosmic equilibrium. They are reminders that motion gains meaning only through its contrast with calm. If you picture the universe now, imagine not the whirling of galaxies or the blazing of stars, but the spaces between, vast regions of steady expansion where nothing collides, where particles drift for billions of years in quiet harmony. Those still expanses are as real as the brilliant ones. They are the universe at peace with itself. Rest, on every scale, is not the absence of energy, but its perfect arrangement. It is the pause that sustains continuity, the quiet interval that gives shape to motion. The cosmos does not rush. It alternates between creation and calm, between the roar of birth and the hush of balance. To recognize those moments is to see the full rhythm of existence, the steady heartbeat of a universe that moves, then pauses, then moves again, forever. Among the countless planets drifting through the galaxy, a small number exist in conditions gentle enough for life. These are called habitable worlds, places where temperature, chemistry, and stability converge in just the right balance. They orbit their stars at distances that allow water to remain liquid, neither boiling away nor locked forever in ice. This delicate range is known as the habitable zone, a narrow band where the possibility of biology can take root. Our own planet, Earth, sits comfortably within such a zone. Here, sunlight provides warmth without destruction, and the atmosphere traps enough heat to sustain liquid oceans. This balance is no accident, but the outcome of physics: distance, mass, rotation, and composition interacting in harmony. If Earth were only a little closer to the Sun, its water would evaporate. A little farther, and it would freeze. Yet temperature is only one part of the equation. For life to thrive, a planet needs a stable climate, a protective magnetic field, and the geologic cycles that recycle nutrients and maintain an atmosphere. Beyond our solar system, astronomers have discovered thousands of exoplanets, worlds orbiting distant stars. Some are hot gas giants hugging their suns, others are rocky and cool, more like Earth. Using methods such as the transit technique, measuring the minute dimming of starlight as a planet passes in front, scientists can determine size, orbit, and sometimes even atmospheric composition. Among these distant discoveries, a small but growing number lie within their stars' habitable zones. They are potential homes for liquid water, and perhaps for life. Not all habitable environments orbit within classic zones. Moons like Europa and Enceladus, circling Jupiter and Saturn, lie far from the sun's warmth, yet conceal oceans beneath their icy crusts. Heat from tidal flexing, the stretching and squeezing caused by gravitational pull, keeps these hidden seas liquid. Geysers on Enceladus have even been observed spraying water vapor and organic molecules into space, direct evidence of chemical activity in a place far beyond sunlight. If life can exist there, it would suggest that the universe's habitability is not confined to narrow conditions but woven deeply into its nature. The search for habitable worlds extends beyond curiosity. It is a reflection of connection. When scientists point telescopes toward other stars, they are not only collecting data, they are tracing the same ingredients that formed our home. Every planet found affirms that Earth is not an exception but part of a pattern. The elements of life, carbon, hydrogen, oxygen, nitrogen, are abundant everywhere. The chemistry that gave rise to living systems here could, in principle, unfold elsewhere wherever conditions align. Still, habitability does not guarantee habitation. A world may be perfect for life and yet remain lifeless. The transition from chemistry to biology may require events so rare that they have occurred only once. Or it may be inevitable, waiting only for time. Either way, the search teaches humility. In studying other worlds, we learn how fragile and rare our own balance is. A planet small enough to cool, large enough to hold an atmosphere, distant enough to rest safely beneath a stable star. Earth's habitability has persisted for billions of years, maintained by a subtle feedback between rock, air, water, and sunlight. This resilience is not eternal, but it reminds us that stability is possible even in a changing cosmos. Whether life exists elsewhere or not, the same natural laws that sustain it here apply everywhere. The search for other habitable worlds is therefore also a mirror, showing us the fine harmony of our own. As you think of these distant planets, imagine each as a point of light circling its star, quiet, patient, and waiting. Some may already harbor oceans and skies, others may only dream of them in potential. Each is part of the same grand experiment, the universe testing combinations of warmth and time. And somewhere among them, perhaps, another world looks up into its own sky, wondering, just as we do, whether it is alone. For generations, humanity has looked into the night sky and asked a simple question. If the universe is so vast and full of stars, where is everyone? This is the essence of the Fermi paradox, the puzzle that arises when we combine the enormous number of potentially habitable worlds with the apparent absence of any signs of advanced civilizations. The silence of the cosmos is not just quiet, it is profound, stretching across billions of years and trillions of miles without a single confirmed reply. Statistically, life seems almost inevitable. The Milky Way alone contains hundreds of billions of stars, many with planets in the habitable zone. If even a tiny fraction of those planets developed life, and a smaller fraction of that life became intelligent, the galaxy should be alive with communication. Yet our radio telescopes detect only natural signals, the hum of pulsars, the hiss of cosmic background radiation, and the faint static of distant stars. Not once have we intercepted a deliberate transmission or seen technology glint unmistakably in the dark. Several explanations have been proposed, each as haunting as it is plausible. Perhaps intelligent life is exceedingly rare, requiring a chain of coincidences so specific that it occurs only once in a galaxy, or even once in all of existence. Or perhaps civilizations arise frequently but vanish quickly, extinguished by natural disasters, wars, or the exhaustion of their own resources before they can reach the stars. In this view, silence is not absence but aftermath, a record of countless voices that have already fallen quiet. Another possibility is that we are simply not listening in the right way. Civilizations far older and more advanced might use technologies beyond our comprehension, quantum communication, neutrino signaling, or gravitational encoding, methods invisible to our current instruments. Their messages might fill the universe even now, but we have not yet learned to recognize them. There is also the notion of the Great Filter, a theoretical barrier in evolution that most forms of life fail to cross. It could lie behind us, the rare leap from chemistry to consciousness, or ahead, as a challenge no civilization survives. If the filter is still to come, then our silence may be a warning rather than a mystery. Yet the absence of evidence can also be interpreted more gently. Perhaps the cosmos is full of life, but distance and time keep us apart. The speed of light, the universe's ultimate speed limit, makes communication between stars painfully slow. Even if another civilization were to broadcast a message, it could take centuries or millennia to arrive, and we might not even exist to receive it. In the grand timescale of the universe, our moment of listening has only just begun. The search continues. Projects like SETI, the search for extraterrestrial intelligence, scan the skies for structured signals, repeating pulses, or narrow-band emissions that nature rarely produces. Others look for indirect signs, atmospheric chemicals that might indicate industry or global energy use. So far, all results point to a quiet cosmos, but the effort itself remains one of humanity's most patient acts of curiosity. There is beauty in this patience. The silence is not empty, it is filled with possibility. Listening teaches humility. It reminds us that we are newcomers in a universe that has been unfolding for billions of years. Perhaps we are among the first to awaken, or perhaps countless others have already listened and wondered in their own skies. As you think of this, imagine that the stillness around Earth is not loneliness but anticipation, a pause in a symphony before the next note sounds. Somewhere, light continues to travel from distant civilizations that may have risen and fallen before our world even cooled. Their signals, faint but persistent, could be crossing the darkness even now, waiting to arrive in some future age when new minds are listening again. Across the immense span of time, the universe displays a quiet patience. Stars burn, galaxies drift, and whole epochs pass with the slowness of thought. Yet among all cosmic rhythms, one theme endures above the rest: longevity. From the smallest particles to the largest clusters, existence favors endurance over haste. Creation's brilliance is often brief, but its persistence is eternal. Not all stars share the same lifespan. The most massive live spectacularly but die young, blazing through their nuclear fuel in only a few million years before collapsing in supernovae. In contrast, small, cool red dwarfs burn with moderation. Their fusion proceeds slowly, wasting almost nothing. Some may shine for 10 trillion years, far longer than the universe has yet existed. Long after the bright blue giants fade, these modest stars will remain, quietly illuminating the dark with a patient glow. Galaxies, too, embody this endurance. They are not static, but their transformations occur over billions of years. Collisions and mergers reshape them without erasing their identity. When two galaxies unite, their stars pass through each other without direct collision, their combined gravity settling into new order. The Milky Way itself will one day merge with the Andromeda Galaxy, forming a larger system that will persist for eons, even as the wider universe grows colder and more diffuse. Endurance exists even in the smallest building blocks of matter. Protons, the core particles of atoms, appear to be nearly immortal. Experiments searching for their decay have found no evidence of disintegration, suggesting that they may last for at least 10 to the power of 34 years, longer than all the stars, longer than galaxies themselves. In that distant future, when even light has thinned, these subatomic survivors will still carry the imprint of the early cosmos. This tendency toward persistence shapes the universe's story. The processes that endure the longest are not the loudest, but the most stable. Stars that burn slowly, galaxies that evolve gently, and atoms that barely change, all ensure that time continues. The cosmos does not seek permanence through resistance, but through balance. Its longevity arises from harmony between energy and gravity, between motion and rest. For humanity, accustomed to brief lifespans, these timescales are difficult to grasp. 1 trillion years is a number without emotional weight, yet it defines the future that awaits the stars. Even when the last red dwarfs eventually exhaust their hydrogen, they will cool into faint embers called black dwarfs, radiating the final whispers of starlight into an expanding dark. By then, the universe will have entered an era of quiet endurance, a slow, timeless persistence where change occurs only through decay and chance encounters. Some scientists call this distant era the degenerate age, when ordinary matter remains but energy exchange nearly ceases. Galaxies will fade, planets will wander free, and only faint radiation will remain. Yet this is not an ending. The universe will still exist, held together by the same laws that have guided it since its beginning. Even as entropy rises and temperature falls, the fundamental structure will persist, space expanding, particles moving, gravity still shaping the faint echoes of what once was bright. There is calm in that vision. Longevity brings perspective. The same patience that sustains red dwarfs and protons also sustains the universe itself. Time, on cosmic scales, is not a river rushing to its end, but a vast ocean whose surface ripples slowly, almost imperceptibly. As you think of this, imagine yourself within that continuum, not separate from it, but made of the same enduring matter. The atoms in your body are ancient, their lifespans far exceeding your own. They will travel on long after you, joining stars, dust, and new worlds yet to form. In that way, you already share in the universe's longevity. Existence does not fade, it transforms, carrying every particle forward through time's long, steady heartbeat. Though the universe moves toward greater entropy, it never truly stands still. Even within decay, there is rhythm. Matter and energy flow through cycles of transformation that repeat across every scale of existence. Stars die, but their ashes form new suns. Galaxies collide, yet from their wreckage rise new systems of order. This eternal renewal is one of the universe's most beautiful qualities, the continuity of creation through change. The story begins with stars. Inside their cores, nuclear fusion forges elements from simple hydrogen, building heavier atoms that serve as the raw ingredients of future worlds. When massive stars exhaust their fuel, gravity crushes them until they collapse or explode. In these supernovae, elements are hurled into space: carbon for life, iron for planets, gold for minerals deep within their crusts. Each explosion may seem destructive, but it is an act of distribution, scattering the ingredients for new beginnings. The calcium in bones, the oxygen in air, the iron in blood, all were born from these stellar deaths. Over time, clouds of gas enriched by such remnants gather again under gravity's pull. They cool, condense, and give birth to new generations of stars. Around those newborn suns, disks of dust and gas coalesce into planets. Some of those planets, in turn, may nurture life, which alters its environment through chemistry and time. When life dies, its atoms return to the planetary system, to the stars, to space itself. In this way, the same material that once formed distant suns now circulates through living organisms, forming a bridge between the cosmic and the intimate. Galaxies follow a similar rhythm. They grow by merging, their stars mingling like currents blending in a river. Collisions compress gas and dust, igniting bursts of star formation. Later, the merged system settles into calm once more, only to repeat the cycle when another galaxy drifts close. The cosmic web itself, those filaments that span billions of light years, continues to evolve as matter flows along its threads, gathering where gravity is strongest, thinning where expansion prevails. Creation and dissolution, expansion and balance, the pattern echoes endlessly. Even on planetary scales, cycles prevail. Water evaporates, falls as rain, and returns to the sea. Carbon moves from rock to atmosphere and back again. Energy from the sun flows through ecosystems, powering life before radiating back into space as heat. Nothing is ever static. Everything participates in a system of exchange. The universe's persistence lies not in permanence, but in transformation. In physics, this principle is captured by the law of conservation. Energy cannot be created or destroyed, only changed in form. Every photon emitted, every motion, Every thought is part of this circulation. When energy leaves one system, it enters another. When a star collapses, it releases radiation that travels for billions of years, perhaps to warm a world where something new begins. The cosmos continually recycles itself, not in defiance of entropy, but in harmony with it, spreading complexity through the very process of dispersal. For humanity, the same law holds meaning beyond science. Renewal is not limited to stars and galaxies. In our own lives, cycles of growth and rest, creation and release, follow the same quiet rhythm. What ends often becomes the seed of what begins again. Even memory and knowledge move in patterns, passed from one mind to another like starlight crossing generations. As you picture these cycles, imagine the universe breathing, a vast, slow inhalation and exhalation that spans eons. Each phase of expansion gives way to calm, each collapse gives birth to new order. The atoms that compose you are part of this timeless rhythm, older than Earth itself, and destined to wander on. Nothing in nature truly disappears, it only changes its role in the story. In the grand design of space without borders, the universe's power lies not in endless creation, but in endless renewal, a rhythm of transformation that ensures nothing is wasted, and everything, sooner or later, shines again. In all the vastness of space, among stars and galaxies that stretch beyond comprehension, one phenomenon stands apart: awareness. Somewhere within the dust of collapsed stars, matter learned to think. Through the quiet chemistry of life and the slow unfolding of evolution, the universe achieved the ability to look back upon itself. Human consciousness, small, temporary, and fragile, is the cosmos reflecting on its own existence. It is easy to feel insignificant in the face of such immensity. The distances are so great, the timescales so long, that our lives appear like flickers of light that vanish almost as soon as they begin. Yet it is precisely that brevity that makes awareness precious. In a universe governed by impersonal laws, life introduces perception, memory, and meaning. The atoms that once moved blindly now participate in observation. Through our senses and instruments, the universe studies itself. Every act of wonder is a continuation of the same curiosity that drove early humans to map the stars. When Galileo turned his telescope skyward, he extended the reach of the universe's own vision. When radio telescopes captured signals from distant quasars, the cosmos, through us, listened to its own echoes. Each discovery, every photon measured, every particle traced, is a dialogue between existence and awareness. Humanity's science, though limited, reveals a deep kinship between the individual and the infinite. The elements that shape thought and emotion are ancient. The calcium in our bones was born in long-dead stars. The oxygen we breathe was forged in their cores. The carbon in our cells once drifted as cosmic dust before finding form in life. Even consciousness itself, though intangible, is a structure of energy and matter, a pattern of electrical impulses shaped by the same physical laws that bind galaxies. The urge to understand, then, is not separate from nature, it is its continuation. Curiosity is the universe's way of exploring itself from within. When a child looks up and asks why the stars shine, the question is not posed by an outsider, but by matter becoming aware of its origins. Wonder is the bridge that unites the scale of atoms with the scale of galaxies. Science often speaks of observation as detached, but true wonder carries emotion, a sense of belonging that turns knowledge into reverence. To study space is not merely to collect facts, it is to feel the quiet astonishment of being part of it. Each new discovery, from black holes to exoplanets, deepens that connection rather than diminishing it. The more we learn, the clearer it becomes that everything, light, matter, thought, is woven into the same continuous fabric. And though humanity is still young in cosmic terms, its awareness already extends farther than its physical reach. We have measured the age of the universe, mapped its background radiation, and traced its evolution from a hot, dense beginning to the expansive calm we inhabit now. Yet knowledge does not erase mystery, it multiplies it. Each answer uncovers deeper questions, reminding us that understanding is infinite and that wonder is not a step toward closure but a permanent state of discovery. When you think of your place in the universe, imagine not a lonely figure beneath indifferent stars, but a participant in their light. Every glance upward completes the circuit of existence, the observer meeting the observed. The universe is not silent. It speaks in patterns, in beauty, in the quiet logic that draws us to explore. In the end, wonder is what keeps the cosmos alive within us. It transforms cold distances into connection and turns observation into meaning. To feel awe is to align, briefly, with the rhythm of creation, to sense that the same energy flowing through galaxies also flows through thought. The stars do not need us to shine, but through us they are seen, and in that act of seeing, the universe becomes aware of its own magnificence. We have followed the story of the universe from its first light to the quiet depths of time, tracing its rhythm of birth, motion, and renewal. What began as energy has become matter, and what began as simplicity has grown into complexity and awareness. Space stretches outward, still, calm and unbounded, carrying galaxies like lanterns across an ocean that has no shore. The story has no true ending, only pauses, moments of stillness where understanding meets peace. The universe around you remains vast, but it is also continuous with you. The atoms in your body were once the fuel of stars, cooled, scattered, and gathered again into living form. The air you breathe, the light that warms you, and the gravity that holds your world together all trace back to the same moment when time began. You are not apart from the cosmos. You are an expression of it, a temporary arrangement of its elements, aware of itself for an instant in the long flow of existence. Each part of the universe moves according to the same principles: expansion, gravity, transformation. Stars burn and fade, galaxies merge and drift, and space itself continues to widen. Yet within that endless motion lies order. The laws that govern particles and planets never falter. The constancy of those laws allows the universe to change without chaos, to renew itself endlessly while remaining whole. The same harmony that guides distant galaxies also sustains the pulse of your heart and the structure of every atom you carry. When we call this vastness space without borders, we acknowledge that there is no edge to what exists. There is no outside and no boundary, only continuity. Every horizon reached reveals another beyond it. The universe expands not into emptiness but into itself, creating more room for possibility. Infinity, in this sense, is not a number, but a state of openness. It is the natural posture of reality, always unfolding, never complete. Humanity's place within this vastness is small in scale, but immense in meaning. To observe the universe, to measure its age, and trace its origins, is to bring consciousness into the equation of existence. Through curiosity, the cosmos becomes more than mechanism. It becomes experience. Each question, each act of observation, extends the universe's awareness of itself. Through science and imagination, you participate in that expansion, joining the great act of seeing that began when the first eyes turned toward the stars. And yet, beyond all discovery, there remains quiet. The space between galaxies is filled with silence that no vibration disturbs. In that stillness, the universe rests, vast but not empty, alive but at peace. The same stillness exists within you, waiting beneath the movement of thought. If you listen closely, you can feel the two silences align, the outer and the inner, the cosmic and the human. They are not separate silences, but one. You have journeyed through creation's story, the birth of light, the curvature of space, the endurance of stars, and the patience of time. Now the path returns to calm. There is no need to hold each detail. They are already part of you, like starlight absorbed into memory. Knowledge has settled into stillness, and stillness, in turn, has become understanding. The universe continues its quiet expansion. Galaxies move, stars evolve, and the deep background hum carries on beneath the silence. But for now, you can rest within it, knowing that you belong to it completely. The same continuity that binds galaxies binds you. The same energy that lights distant suns sustains every heartbeat. If drowsiness has come, let it stay. If wakefulness remains, that is fine too. The purpose is not to drift away, but to rest in awareness of the infinite, the calm recognition that you are part of something without edges, without borders, and without end. We from Sleepy Stories wish you a good night.